Okay, so we're going to be talking about a project, a science project we can do at home that shows the passage of time since we've all been locked up since the COVID lockdown started. It's a solar calendar. So this is also something that, say, hypothetically, you fell asleep for a long time and you woke up and you didn't know what day it was and civilization had ended and so you couldn't look it up on a computer. You could measure the angle, or you could measure the length of a shadow, and if you knew where you were on the Earth's surface, you could figure out what day of the year it was. Okay, and so what we're doing is measuring the length of shadows, and we're doing that every day. And we can see that as we move from the equinox, which was roughly when the lockdown started, towards the solstice, which was the day when the sun is highest in the sky, we're seeing that the shadows get shorter and shorter when measured at high noon. So that's the time of day when the sun is highest in the sky, so when the shadow is shortest. Okay, so to explain why the shadow gets shorter, we'll draw a diagram. So here's the Earth. Okay, so we'll make the Earth's rotation axis vertical like this. Okay, so the Earth's equator is defined as being 90 degrees to the rotation axis. So if we, or put ourselves in Saskatoon where we live, okay, that's at 52 degrees latitude, so that's somewhere about here. Okay, and if say we want to draw something that's vertical, so that's sticking straight up, one way of doing that is to draw a line to the center of the Earth. Okay, so this represents what for us is our windowsill or whatever it is that's casting the shadow. Okay, so we'll consider a couple of situations. So we'll consider the equinox, which was roughly when the lockdown started. Okay, so on the equinox, the equator, or the Earth's, or the ecliptic, which is the plane with which the Earth revolves around the sun, okay, lies on the equator. Okay, so it looks like this. Okay, so this is the equinox. So this is the ecliptic at the equinox. Okay, and all the sun's rays come in parallel to the ecliptic. Okay, so there's a series of sun's rays, so including this one up here. Okay, so the one that intersects the Earth's surface, or excuse me, intersects the top of our windowsill, which is what's casting the shadow. Okay, and so we can see then that that ray, the one that just grazes the top of our windowsill, will hit here, and so the length of the shadow will be this. Okay, so we're going to measure that later. We'll call that little L, and we'll call the height of what's casting the shadow big L. Okay, so we'll contrast that with, say, the solstice. So the June solstice is when the Earth's rotation axis is actually tilted directly towards the sun in the north. Okay, and so at that point then, the ecliptic, instead of being in the equator, is actually above the equator. Okay, it's up like this. Okay, so here is the ecliptic at the solstice. Okay, and so the sun's rays come in parallel to the ecliptic. Okay, so on the solstice then, they're coming in so parallel to this line here, so something like this. Okay, and so we can see then the ray that just grazes the top of the windowsill now hits over here. Okay, and so we can see then that red line, this red line here, is longer than the green line here. Okay, so we can see then that the shadow is getting shorter. Okay, and we can look at that a little bit mathematically. Okay, so in terms of, or at the equinox, this angle here is just equal to the latitude, which we'll call lambda. We use the Greek symbol lambda. And you notice then, if you consider this triangle made by this red line here, as well as the blue stick here, that's actually the same as this angle here. Okay? And so we can then also look at the angle that the sun makes to the horizon, which is given by this angle in here in this triangle. Okay, so if we call that angle phi, okay, we can see that actually for either time, we can get that angle phi by measuring the length of the shadow and knowing the height of what's casting the shadow. And that relationship is that the tangent of phi, if you know trigonometry, is equal to big L divided by little l. Okay, and that's true all the time. So at the equinox and at the solstice and on every day in between. Okay, so we can work out what that angle phi is on any day. Okay, so specific to the equinox, we can work out what that angle phi is. Okay, so phi Okay, so we can see it's just equal to, in that case, it's just equal to 90 degrees minus the latitude. Okay, looking at this, we can see that because this is a right angle triangle, it's just, we add up the interior angles of a triangle, they have to be 180 degrees. That tells us that phi must just be 90 degrees minus lambda at the equinox, which in Saskatoon is 90 degrees minus 52 degrees, which is equal to 38 degrees. Okay, whereas at the solstice, what happens then is that this angle here, so here's the ecliptic, okay, it's now tilted relative to the equator by what's called the obliquity, which is 23.5 degrees. We'll call that A for now. Okay, and so we can see now that the angle here, this interior angle, is equal to the lambda minus A. Okay, so it's the latitude minus the obliquity. Okay, and so that tells us then that the angle above the horizon, which we'll still call phi, is 90 degrees minus lambda minus A, which is equal to 90 degrees minus lambda plus A, which is equal to 90 degrees minus 52 degrees plus 23.5 degrees, which is equal to 61.5 degrees. Okay, so we can see that there's a significant difference in the angle above the horizon at the equinox and at the solstice. And we'll see if we can measure that by measuring the angle of the windowsill. The length of the shadow cast by this south-facing window when it's at its shortest, which is solar noon, which here in Saskatoon, that's about 1:10 in the afternoon. So Daphne, do you want to come help me measure here, sweetie? So the height of the windowsill is 67.5 centimeters. Okay, so what we're measuring is the length of the shadow. So here you can put it down, and the other thing we do is we line it up with the edge of the shadow. Line it up here, honey. So, and it's got to touch the wall.
It is.
Okay, so we line it up with that so that we know we're getting the minimum length. Okay, and so we can measure, and right now, as of today, it's at, when do you want to read that off? I think that's actually 57.6. Oh, you're right, 47.6, my bad. Okay, so today it's 47.6 centimeters, whereas the height is 67.5. And so right now, because the sun is above 45 degrees in the sky, the length of the shadow is quite a bit shorter than the height of the windowsill. So we can calculate the height of the sun in the sky from the length of that, or from the ratio of the length of the shadow to the height of the windowsill. Okay, so we're now going to take a look at the data that we measured by measuring the length of the shadow from the windowsill. Okay, so we'll take a look at this graph here. So what we can see, that plotted are the red asterisks or data points. So the first data point was measured on March the 29th. The last one we've done so far is on May the 7th. Okay, and we can see then that over that time, the length of the shadow cast by the windowsill has decreased from just under 75 centimeters to about 47 centimeters. Okay, so it's decreased by about 28 centimeters over the course of that 6 weeks or so. Okay, the blue line on this graph shows what we would predict the shadow change would be just based on knowing the angles and doing some trigonometry. Okay, so that's the length of the shadow. We can then convert that to an angle. Okay, and that's what's shown here. Okay, and so we can see that when we started making the measurement, it was about 42 degrees. Okay, and then as we've continued to make measurements, the angle of the sun has got higher and higher in the sky. Okay, and the last day we took a measurement, it was about 55 degrees. Okay, so it's changed by about 13 degrees in that time. Okay, so the last thing we'll look at is what we'd expect it to look like over the course of a year. Okay, so this is how the angle of the sun in the sky will change over the course of a year. So this is where we'll hit the summer solstice. Okay, we'll hit the fall equinox here. This is the winter solstice, where you can see the angle will get extremely low. And the red asterisks are the measurements so far. Okay, so we can see now the increase of the angle above the horizon as we're approaching the solstice. Okay, so that's how we can make a solar calendar. Okay, so we can also see though that there's 2 days each year that the where we are that the shadow will have the length it has. But if we know that the shadows are getting longer or getting shorter, we can tell which one is which. So we can tell which day of the year it would be. Okay,